see the periodic trends in atomic and ionic radius, how it will vary in the groups and period. Before that, what is the structure of atom? From our childhood we are studying atoms having this type of structure. It's like a circle and in the center there is nucleus and electrons are revolving around the orbitals. Is it true? Is atom is like a circle? No, it is wrong. And we cannot determine the exact position of electrons because electrons are always revolving, isn't it? And it is always revolving around the nucleus. So we cannot predict the exact position of electrons, isn't it? And electrons are in this not exact one electron. It is in the form of the what? It is in the form of a cloud. Here you can see. Actually, it is the structure of an atom. Here the center of nucleus will be there and electrons will be like a cloud around the nucleus. So we cannot predict or we cannot determine the exact position of electrons. And we know that atom is really small. We cannot see atoms with our naked eyes, isn't it? And we know that we cannot pick one atom and we cannot measure it, isn't it? So how can we identify the atomic radius of an atom? Here they are given atomic radius of nitrogen is 0.70 angstrom. How can we determine the atomic radius? For determining the atomic radius, we cannot pick one atom, isn't it? So we can measure the internuclear distance between two atoms. So the atomic radius can be classified as covalent radius, van der Waals radius and metallic radius. The covalent radius is the half of the internuclear distance between two bond atoms. Van der Waals radius is used to define the half of the distance between the closest approach of two non-bonded atoms. Metallic radius is the radius of from the nearest two metals. For example, you can see the covalent radius. Here you can see the two nucleus, that pink circled, that in the middle you can see a pink circle, isn't it? That is nucleus. So here you can see the internuclear distance. If we take half of the internuclear distance, we can find out the covalent radius. So if you check here, you can see these are 70th group elements, that is fluorine, chlorine, bromine, iodine, isn't it? If we check down the group, the atomic radius is increasing. Similarly, if we check the first group elements, lithium, sodium, potassium, rubidium, cesium, these are alkali metals, isn't it? If we check in a group, the atomic radius increases. Why? Why it is happening? What will be the reason? So, for example, if you check a group, what is happening? Here you can see down the group, atomic number is increases, isn't it? Atomic number of lithium is 3, whereas atomic number of sodium is 11, whereas atomic number of potassium is 19. So, moving down the group, what will happen? Atomic number is increases. If atomic number increases, number of shells increases, isn't it? If we check with lithium, it has only K and L shell, only two shells you can see, isn't it? But if you check with sodium, it has K shell, L shell, M shell. If we check with potassium, it will be K, L, M, N shell. So number of shells increases and number of protons, number of electrons increases. So moving down the group, atomic size increases, number of electrons increases, thus number of shells increases. So what will happen? From the center of the nucleus to the last shell, that is, we know that is nuclear distance, isn't it? So nuclear distance also increases. So the attraction of nucleus to the last shell is decreases because there are so many shells, isn't it? So the attraction of nucleus to the valence shell or valence electrons decreases down the group. Thus, atomic radius increases down the group. So, do you understand that? For example, in a classroom, in your classroom, the teacher will be in the front. The last bench students will show some naughty things, isn't it? They will always show some naughty things, or they will be some kind of lazy. Because why? The teacher is near to the first bench students. So, the distance between the teacher to last bench students will increases, isn't it? So, the concentration between the last bench students and teacher also, is it increasing? No, decreases. Teacher cannot give much concentration on last bench students. So they will do some mischievous thing. But in a good teacher or in a good classroom, if all are good students, it will not happen. I hope all of you are very good students. So these all things will not happen in our class. Okay. So the next point. Here you can see the atomic radius of third period element: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. So those are third period elements, isn't it? If you check the atomic radius is increasing. Is it increasing? No, it is decreasing. Why? What will be the reason? So let's check here. Here you can see the third period elements, isn't it? Sodium, silicon, chlorine, argon. The last row. The last horizontal row, if you check, their number of electrons are increasing. In sodium, the last shell, if you check, only 1 electron. But if silicon, it is 2 electrons. For chlorine, it is, how many electrons are there? Chlorine, it is 7. Is it 7? For sodium, it is 1. Silicon, it is 1, 2, 3, 4. Chlorine, it is 7. Argon, it is 8. So, number of electrons are increasing. But number of shells are not increasing, isn't it? So, we know that in nucleus protons are there. So, number of protons also increasing. So, the nuclear charge also increasing. But the nuclear charge increasing and number of electrons also increasing. So, nucleus has high attraction on the valential electrons. So, thus, as the number of protons are increasing in the nucleus, it has the ability to attract the valential electrons, isn't it? So, number of shells are not increasing. They all have only 3 shells, isn't it? So, number of shells are all having KLM shells, isn't it? So, what will happen? The nuclear attraction on the valence shell also increasing because of the increasing the number of protons. So, what will happen? The size decreases along the period. So, what is the general trend in atomic radius? Down the group, atomic radius increases, and along the period, atomic radius decreases. Then let's go to ionic radius. What is ionic radius? It is the distance, it is the internuclear distance between anion and cation. What is anion? What is cation? If an atom donates electron, it became cation. If an atom accepts electron, it became anion. Here you can see cation and anion. So here you can see some cations and anions and the ionic radius. Here you can see the red colored balls like round are ions, that are cations which carrying positive charge, isn't it? That the blue color is anions and the parent atom is in like a type of brown color. light green color, isn't it? So the size of the cation is smaller than parent atom, but size of the anion is larger than which atom? Parent atom. Why? Because we know that cations will donate electrons, isn't it? If it is donate electrons, number of electrons decreases, but the number of protons in the nucleus will be the same. So what will happen? Protons are more than electrons, so nuclear charge will be more on the valence shell. But in the case of anions, what is happening? Electrons are adding to the valence shell, so number of electrons will increases, but number of protons is lesser than the number of electrons, so internuclear charge will decreases. So thus cations having smaller size than parent atom, but whereas anions having the larger size than the parent atom. And do you know the electronic configuration of isoelectronic series or isoelectronic species? What are isoelectronic species? If you check the electronic configuration of O2 minus, let's write that. What is the atomic number of oxygen? What is that? It is 8, isn't it? 8. So what will be the electronic configuration? 2, 6. But what will the electronic configuration O2 minus? For fulfilling the octet, it needs 2 more electron, isn't it? So it will accept 2 electrons and it will become 2 minus. So what will be the electronic configuration of O2 minus? Will be 1s2, 2s2, 2p6. From 1s2, 2s2, 2p4 it will change to 1s2, 2p6. Here you can see some other elements and ions. What will be the electronic configuration of all of those? If we check with the fluorine, it is also 1s2, 2s2, 2p6. If we check with neon, it's 1s2, 2s2, 2p6. And if you check with sodium, it's also 1s2, 2s2, 2p6. Sodium donating 1 electron and it became the cation. So it will donate electron and it became cation. So these all are having the same number of electrons. Such compounds or such species are known as isoelectronic species. Okay, but why, if they are containing same number of electrons, why they having different sizes? Check. The magnesium is smaller size compared to O2 minus. Why? Because we know that here number of electrons are the same, but the number of protons are vary. So the internuclear distance same, but the internuclear charge will be more. The nucleus charge on the valence shell electrons will be more compared to the sodium to oxygen. If we check with sodium, the number of protons will be more than number of electrons, isn't it? So the nucleus charge on the valence shell will be more. Thus, it is showing different sizes, isn't it? So cations having smaller size compared to the anions. I hope all of you understood this. Okay, thank you.